Everybody always has a problem with IUPAC. Everybody thinks it's so complicated. But, I mean, tell me what you think. In all honesty, we've looked at this yesterday. You've got a root, a suffix, locants, and a prefix. And we've got a lot of work to do with prefixes today, yeah? But is that hard? I mean, we're going to look at the prefixes and see how the prefixes make the name incredibly cumbersome. But it's not challenging. Identify the longest carbon chain, which contains your primary functional group. Determine the root, give it a suffix or suffixes and a suffix stopper, and then look at everything else that is not a part of the parent chain and incorporate it in the prefix. Carly?
So there's a question on the homework, and I think it's wrong because I can't figure it out.
Well, if you can't figure it out, it's definitely wrong.
It's number 13.
Yeah.
But I know, it's so wrong. No, I feel like I'm having a hard time, like, naming it. I don't know why. I'm like, so say you have, like, so depending on how you number it, you can have, like, 2 ethyls or 1 methyl. I guess.
Okay, this is a good question. Yeah.
One take precedence over the other when naming.
Are you saying it's butane or
Yeah.
pentane?
It's pentane.
There's 5.
Yeah, there's a 5
That's what
carbon
that's
chain.
So you do, okay, so then the substituents are coming off the 3rd carbon then?
Did you do this?
That's what I did.
Well, I was trying to number it. I don't know, I tried so many different ways, but I get that. So in my last class, they said, like, I guess I was taught to, like, when you're naming, I guess that way makes sense, but it doesn't come off like the set. I guess, sorry, I don't even know what I'm trying to say.
Okay.
When you're numbering going from, like, the left top one, the top carbon, right, then the substituents are coming off the 2nd carbon, but
That's
if you
true.
number it the way that you were just showing, then I guess to find the longest parent chain. But I guess where does, I don't know, like, does substituents take precedent or the longest carbon chain?
Parent chain, then substituents.
Interesting.
Which is actually why when we did this activity, we started with the root.
Yeah.
To find the parent chain. That's your first goal. Cameron?
So I believe this one started with 3,3 dash. And
Yeah.
I get that it's on the 3rd carbon, but why are there 2 3s written down?
Because there's 2 methyl groups. You had 3,3, but then you also had dimethyl, is that right?
But why does dimethyl not? Why is it not good enough to say dimethyl? Because
I love this
dimethyl
question.
understood.
I love this question because there is no room for ambiguity. There's no room for, did Cameron forget to tell me that the other methyl group was on 2? Or am I just supposed to assume that the dimethyl with only 1 3 in front of it, they're both on 3? There's no room for ambiguity. We're redundant to clarify it as much as possible. There's a methyl group at 3. There's a methyl group at 3. 3 3 dimethyl. So what I would say is the only better option would be to say 3-methyl 3-methyl pentane. Why say methyl twice when you can say 3 dimethyl? And the trend that I'm going to push you guys to do is every substituent you have, every group that comes off of the parent chain has its own locant. Even if the same type of group is present multiple times, even if those multiple groups come off the same carbon, every substituent has its own locant. So if you've got di, I expect to see 2 locants. If you've got tri, I expect to see 3 locants. Does that sound good?
Makes sense.
Okay. We had gotten down to looking at our prefixes, and I want to spend some more time today expanding this category alkyl. Notice that ALK, I talked to you guys about this at the start of the week. Alkane, alkene, alkyne. That ALK is a really good indicator of a carbon group. And then this YL is a suffix that tells me substituent of. So I'm not going to have ein, een, or ein in a prefix. I'm going to have YL. Unless it's a halogen. And then the halogens get spelt with the first part of their name followed by O. So we call these the halo groups. Fluoro, chloro, bromo, iodo. Do you guys remember that aldehydes and ketones show up in the suffix? Aldehydes are represented with Al. Ketones are represented with -one. But they're not the highest priority functional group. So if they are present with a carboxylic acid, they can't show up in the suffix. They have to be designated as a substituent. They have to show up in the prefix. So they get this term oxo. And what about alcohols? Alcohols change the suffix. What suffix do they give the compound? OL, all, for alcohol. But what if there's a ketone or an aldehyde or a carboxylic acid, a higher priority functional group? The alcohol cannot appear in the suffix. It still has to be designated. And so it shows up as a substituent. In our class, alcohols will be the highest priority functional group. Once you get into OChem 2, then you'll be tested on nomenclature with aldehydes, ketones, carboxylic acids, and the alcohol has to be a substituent. But I do want to give you a perspective, a heads up. There is a bonus assignment on nomenclature. This goes towards your homework. If you scroll down to the bottom here of our unit, PLO2, and let's just take a look at this. For reference, this is not my assignment. So this does not resemble the assignments that you will see, the types of questions that you will see. But in my spring and fall semesters, I'm required to grade this and report it to the department as an assessment across all of our sections. And I don't want to gyp you guys for things that my other sections have to do too, so I'm giving you the option to get these bonus problems. Just clarifying, they're not really going to align with the types of problems you'll see here. There is a section here where you are asked to name some of these compounds as substituted alkane compounds. And I could swear that there was a question that had an alcohol in it, and I feel like I'm missing it. Yeah, I'm not sure. Well, anyways, let's take this for example. This compound has an alkane chain, but it also has a possible alkene chain where it takes on that alkene. The assignment wants you to name this as a vinyl substituted hexane chain. But true nomenclature would say, find the longest carbon chain that includes the alkene, and then name this as an ethyl substituent. So just to be aware, there are proper names for these compounds, but the assignment is meant to have you identify an alkane chain and just name everything else as a substituent of that. So let's talk about some substituents. I want to start with a few of the maybe more odd alkyl substituents, ones that involve other functional groups. We've got our aromatic ring. So I'm going to show this as my aromatic ring, and then I'm going to have a bond coming off of it, and I'm just going to show that this is the point of attachment to my parent chain. This ring can also be abbreviated as phenyl, PH, and that is the name that it's given. The substituent name becomes phenyl, YL, to indicate phenyl. There is this vinyl group. That's an alkene that attaches at one point to the parent chain, and the name given to it is vinyl. And then there's this allyl group, which is also an alkane, but it's connected, it's also an alkene, but it's connected to the parent chain by this sp3 hybridized carbon. And that name is just given allyl. So for instance, you could have let's just look at a couple of examples. 2-phenyl pentane. The 5-carbon chain we'll call our parent chain, and the substituent, the aromatic ring, is coming off of position 2 when I number it from left to right. That gives me a lowest locant set. Or let's take this 6-membered ring, and we'll have these two groups come off of it, a vinyl group and an allyl group. What is the root that I'll give to this compound? Cyclohex, suffix ane. And that's because these groups, we're going to call them substituents to this larger 6-membered ring. Now I've got two substituents, allyl and vinyl, and those are going to go alphabetical in my name. So this will be allyl. I'm going to leave a space here. Vinyl, cyclohexane. And now I need to describe where along the carbon chain those two groups show up. In a ring, I get to start numbering anywhere I want. So I'm going to number here, and then find the direction that gives me the next substituent at its lowest position here. Could I have done that differently? I sure could have. I could have started numbering here, and then numbered the other direction. What I have right now is a tied locant set. I want to take a step back. Looking at this 2-phenylpentane, I think you guys would agree that I could have numbered this the opposite way, and I would be left with either a locant 2 or a locant 4, and I'm going to choose the lowest locant 2. Here I still have, it's not just one locant, it's a set of locants. And those locant sets are identical, 1, 2, 1, 2. In the case of a tied locant set, especially for groups that are equal priority, which is going to be, for us, every group is going to be equal priority. Then you give the lowest locant to the first alphabetically. Allyl comes before vinyl. So I'll number this in such a way that allyl gets the lower locant. That's just the way that we'll do it. So then the name becomes 1 allyl, 2 vinyl cyclohexane. Those locants are used to show me where along the parent chain my groups show up. On the next page, I've actually got some rules. One of them down here, number 3, it's kind of a good one for us to fill in right now. It says these, I don't have any commas. You know what? It's not a good one for us to fill in right now. We'll come back to it. Okay, I want to take a minute to look at other alkyl substituents. So a 1-carbon chain gets the substituent name methyl. And in a drawing, that can also be abbreviated as an ME group. We'll just kind of say, you know, we can show CH3 or we can show ME. A 2-carbon chain is an ethyl group, which can sometimes appear in a molecule as ET for ethyl. When we get to the 3-carbon chain, there are 2 ways that it appears. One of them is a straight propyl chain. Sometimes that's called propyl, sometimes it's called N-propyl. You know what, I'm sorry. I feel like my formatting is not very good. I know I'm going fast and you guys are struggling. I'm gonna say how this appears. I don't know why I didn't do that. So once again, we're gonna have our parent chain and then the attachment to this group. And there's 2 ways this can appear. A 1-carbon chain shows up as a CH3 group, or a 1-carbon chain shows up as methyl. A 2-carbon chain, well, there's a few ways this can appear. Condensed formula, or the parent chain connects to bond line 1, 2. I'm going to highlight that by drawing it a little bit bigger. Do you guys understand what I'm doing with the squiggly line?
I'm just wondering, is that one bond that has the squiggly line cutting it, but it's just one bond
Mm-hmm.
from a C to a C?
Yeah, so parent chain carbon to the 2-carbon group. But this can also be abbreviated as ET to show that it's an ethyl group. So this is kind of similar to a condensed structure. It's an abbreviated structure. Do you guys like that or not like it? It's not going to change how I do anything. I'm just curious what you think. You don't like it? It's okay. In my opinion, I like ET better than the bond line because the bond line is not so long that it's almost worth drawing it, but it's so short it looks a little awkward. So ET, to me, kind of sums it up real nicely. So propyl, a 3-carbon chain, otherwise called N-propyl. Here's how it appears. The parent chain connects to this 3-carbon group. And again, we could abbreviate this as CH2, CH2, CH3, or we could abbreviate it as PR for propyl. But there's another way that a 3-carbon chain shows up, and it's called isopropyl. You guys see all of our substituent names end with YL. That's the suffix that tells us substituent. The way that isopropyl connects to the structure, that 3-carbon chain connects at the center of the 3 carbons. It creates this little Y group, and that's how I like to identify the isopropyl groups. You look for this little Y at the end. Here's another common way that you'll see this abbreviated. CH, CH3, 2. It's that 1 carbon of the 3-carbon chain that has 2 methyl groups coming off of it. Isopropyl is considered a common name. There is a systematic way to name a branched branch. Its systematic name is, in parentheses, 1-methyl ethyl. That is, it's a substituent of 2 carbons that has a substituent of 1 carbon coming off of the first carbon from the parent chain. It might make more sense when we see some of the other ones. So let's look at our 4 carbon chains. There are 4 primary ways that we see 4 carbon chains show up. One of them is the butyl group, or the N-butyl group. And this appears as just a 4 carbon chain attached to the parent chain. We have a sec-butyl group. You guys remember that conversation we had about regiochemistry? Secondary means a carbon that is attached to 2 other carbons. The way that a sec-butyl group attaches to the parent chain is that a secondary carbon in the parent chain, a secondary carbon in the substituent connects to the parent chain. But it's no longer a secondary carbon anymore, is it? Because when this carbon bonds to the parent chain, now it's bonded to 3 carbons. So in order to understand why it's called sec, you have to erase the parent chain and say, look at that point of attachment, it's a secondary carbon. Now let's talk about the other systematic way. Let me give you the other way that it looks. From the parent chain, this sometimes can be written as SDU. BU is short for butyl. S is indicating that it's a sec-butyl attachment. The systematic way to name sec-butyl. How long is the longest chain coming off from the parent? 3. So it's a propyl chain, 1, 2, 3, with a methyl chain coming off of it at the first carbon from the point of attachment. This is a 1-methyl propyl substituent to the parent. Wow. All right. Then there is the isobutyl group. The isobutyl looks a lot like the little Y that we had on isopropyl. At the end of this carbon chain, there's that Y group. That's what I associate with isobutyl. And the systematic name for isobutyl, what do you guys think? How long is the chain coming off of the parent? 3 carbons. And where is the methyl group coming off of? It's coming from the second carbon from the point of attachment to the parent chain. So this becomes 2-methyl propyl. The last one we've talked about is tert-butyl. And this looks like, from the parent chain, a little chicken foot. 3 methyl groups, all attached to the same carbon. Very, very often, you're going to see this abbreviated as TBU, little t, big B, tert-butyl. I'm really running out of space. This is terrible. Need to get me a bigger board. There's another common way you'll see this, which is CH3, 3. So we've got bond line, abbreviated nomenclature, and condensed molecular structure. 3 different ways that we can see a structure represented. I want you guys to be familiar with all of these different ways of drawing a molecule. What would be the systematic name of a tert-butyl group? You got the first part? Good. 1,1-dimethyl ethyl. Now, in all fairness, I don't give substituents in my class that are much larger than 4 carbons. But in the 5 carbon family, there is pentyl, neopentyl. I think there's an isopentyl. There's not really a sec or tert pentyl. At that point, the carbon chain just gets really long and hard to name. So the systematic name is a little bit better. And then when it comes to all of our alkyl groups, I'll just take us through a few, some of the more common. If you've got a 3-membered ring, we take that root, cycloprop, and we add the substituent suffix yl, so now it just becomes cyclopropyl. And as that attaches to the parent chain, it just looks like a little triangle coming on. The same with isobutyl. I think one of the more common substituents you'll see other than cyclopropyl is cyclopentyl. Cyclohexyl, cycloheptyl, cyclooctyl, they can all exist. They're just less common because as the ring size gets larger, it's more likely that it becomes the parent chain. It becomes the longest group in the molecule. Before I erase any of this, I want to come back to this idea of alphabetizing these things. We alphabetize by the first letter. Meth, alphabetized by M. Ethyl, alphabetized by E. Propyl, alphabetized by P. Even if it's N-propyl, it's still alphabetized by P. Isopropyl and isobutyl, common names, these are alphabetized by the I. We say they're common names because they're not systematic. It doesn't describe how atoms are connected. It's just something that you have to be familiar with. Iso means little y. Butyl, same thing as propyl, alphabetized by B. But when we look at sec-butyl and tert-butyl, these are not common names. They are systematic names. So for the same reason that we alphabetize N-propyl by P and N-butyl by B, N there stands for normal, just a normal chain, not branched. We're going to alphabetize sec-butyl by B and tert-butyl by B. I know. And ultimately, when you do a name, you don't have to spell out sec and you don't have to spell out tert. You can abbreviate it to S or T. Part of the reason why we don't alphabetize by it. So a couple of oddities there. Isopropyl, I. Sec-butyl, B. What about in the common names? Or excuse me, in the systematic names? 1-methyl-ethyl, 1-methylpropyl, 2-methylpropyl, 1,1-dimethylethyl. Where do we alphabetize there? These systematic names are put into a nomenclature in parentheses. And so all of the other rules go out the window. Anything that's in a parentheses gets alphabetized by the first letter in the parentheses. Methyl, 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 di. D for di. Okay, so we've got this idea of here are the most common substituents. Once we figure out what's in a molecule, we'll alphabetize them. What happens when you have multiple of one group? we use multipliers. And these multipliers go both in the prefix before a substituent, and they go in a suffix before whatever indicates that common group, or that functional group. When you have one of a group, you don't do anything. 2, give it the multiplier die. 3, multiplier try. 4, multiplier tetra. I doubt that we'll see anything more than tetra this semester. But it follows normal naming after that. Penta, hexa, hepta. This is going to be the most common. And then these go right in front of that group. Dimethyl, diisopropyl, trisacbutyl, whatever you've got. Triol, dial for dialdehyde. And in terms of alphabetizing, these prefixes, even though they go right in front of a group, they don't impact alphabetical order. Unless it's in a parentheses. So Jamie came in today and said, is nomenclature the hardest part of organic chemistry? No, but is it convoluted? A little bit, yeah. It is a little bit odd. And my orange is dying, so I'm going to retire him. Okay. Now, we have something that I wanted to talk about when it comes to this one. Multipliers are added when a group is there multiple times. Multipliers do not impact alphabetization. And lastly, you'll notice, especially in this 1,1-dimethyl ethyl group, that we have commas and hyphens. So that's what I want to talk about here. Commas separate what? The locants, the numbers, exactly. Commas separate locants, hyphens, dashes. What do they separate? Yes, so locants versus locants and groups. I'm going to say groups because we can actually see dashes or hyphens in the prefixes and in the suffixes. For instance, we can say pent-to-ene. And so you separate those groups with hyphens from the locant. Or maybe we could say others. Dashes separate locants from everything else. And then lastly, all of our words are never separated. That makes an organic nomenclature name one word with a bunch of numbers and dashes and commas, but there are no spaces in it. We don't have 1,1-dimethyl space, cyclohexanol. We have 1,1-dimethyl cyclohexanol. That I gave the molecule wrong. 3-bromo, 3-methyl cyclohexanol, all one word. I think the longest word in the English dictionary is the name of a molecule, because it's technically all one word. Okay, sorry, I've really been like flipping you guys back and forth on this. This is why I have a hard time doing like an in-class activity, because it's never organized well and I go back and forth. And when I was in college, my OChem professor had handouts for every single section, and it was like, we're not going to look at the middle page, but we're going to do the first and the last, and then we're going to come back to this other section, and then we'll go back to the one that we did on. I'd rather just not do it. So yesterday we were looking at these 8 compounds. Now I want us to determine what are the substituents and what locants would they have. Let's look at compound 1. Can someone tell me what substituent is present? Methyl. And what would be the best locant for it? 2, rather than 4. So we actually have the full name for this compound now. It is 2-methylpentane. That's the compound's name. Compound 2. What substituents are present? Good, we've got a methyl group and an ethyl group. It's going to be alphabetized ethyl methyl. Now, in terms of numbering, the alcohol is the highest functional group, so we're actually going to start there, and then we'll number in such a way that the other groups get their lower locants. So the full name for this compound is 3-ethyl 2-methyl cyclohexanol. We've got prefix, root, suffix, suffix stopper. Carly?
Do you have to put like the 1 at the end?
Yeah, you know what? We're going to spend more time on alcohols in another chapter. No. You don't have to, but it's not wrong if you do. So you could call this 1-cyclohexanol. You could call this cyclohexane 1-ol. Those are both options.
That sounds like ambiguity.
So, yeah, there is an assumption, and I agree. I don't like that assumption. I would rather put it in. But the assumption is that since alcohol is the highest order functional group present, you're going to start numbering at the alcohol. So it is redundant to say that alcohol is position 1. And I agree. I'm not on the nomenclature committee, though. If I was, I'd have some changes to make. Compound 3, what substituents do we have? Ketone is not a substituent. We have 2 methyl groups. So we identified this 8-membered chain as the longest chain, which means that these 2 methyl groups never appear. And where do they show up? Well, I told you guys ketone is the highest order functional group here, so we're going to number from the right to the left so that we hit the ketone first. That puts 1, 2, 3 methyl, 4, 5, 6 methyl. So the name here becomes 3,6-dimethyl oct 4, was it 4 or 5? 5-ene. Oct 5-ene 4-one. Woo! You don't like that? What's that look on your face? Come on. Prefix 3,3-dimethyl, root, suffix, suffix stopper. Everything can get broken down by that. Compound 4. Substituents. A methyl group. On what carbon? We're going to have to start numbering from the alkyne because that's a higher order functional group. 1, 2, 3, 4 methyl. This gives us 4-methyl, 1-butyne. Prefix, root, suffix. We actually already finished number 6. Number 6 is just hexanal, root, suffix, suffix stopper.
On 4, what lets you say 1-butyne, where on 3 you have to say oct 5-ene?
So this alkyne, no, I'm not sure I understand.
So
Why 1-butyne instead of 4-butyne?
Instead of but-1-9.
Ah, okay. IUPAC prefers that locants go right before where their suffix shows up, but doesn't require it. Which means that this could have been called dimethyl 5-octene 4-one. So whatever the first locant is in the suffix could come out front before the root, but the second one can't. Which means that this could be called 4-methyl but-1-ine. Those are both acceptable names, and even your active homework will accept either position. You got a question?
I'm just visualizing in my head.
So there are two places the locant can go. Both of them are accepted, and it's kind of like a whichever one feels better. Okay, number 6. What substituent do we have? What name would we give the chlorine substituent? Chloro. And what locant is chloro located on? Position 2. So we get 2-chlorobutane, which is different from 1-chlorobutane, but there is no 3-chlorobutane. Because if I had 3-chlorobutane, it would have been better to just number the other direction. Any substituents on carbon 3, or compound 7? No substituents. This systematically is called propanoic acid. It probably has a common name that makes no sense, and that's okay. All right, now the last group has 3 substituents. We can say that those 3 substituents don't necessarily have a higher priority than the other. To be quite honest, this is not a compound I'd have you name, but they are some interesting substituents. Bromo, cyano, and this is a meth oxide group, so we call it methoxy, a 1-carbon connected to the parent by an oxygen, as opposed to ethoxy, or tert-butoxy, or isopropoxy, methoxy. So the substituents we get here, bromo comes first, then cyano, then methoxy, and then the root cyclopentane. Let's say that these groups are of equal priority. What's the best way to number them? Why? There's going to be a tie no matter what I do. Right to left gives me 1, 2, 3. Left to right gives me 1, 2, 3. In the event of a tied locant set, tie goes to the first alphabetically, bromine. So therefore, I'll number from right to left.
So if the cyano and methoxy were in swapped places,
Yeah.
would you have 3 cyano, 2 methoxy?
If the cyanide group and the bromine were swapped, then cyanide comes first alphabetically before methoxy.
If that's on number 3 now. So
Well, it depends, right?
because we're still counting from bromo.
Bromine's going to be number 2 or number 2. If I swap these two groups.
I'm sorry, if you switch the methoxy.
Oh, I'm sorry.
Yeah.
No, bromine would still win
And
first
bromine.
alphabetically. Oh, yeah, yeah.
And then you have
1
3
bromine,
3
3 cyano. I do, like, this gets people tripped up sometimes. The locants do not care where they fall in the alphabetical order, unless it's in that case of an alphabetical tie. The locants just are whatever they need to be. The groups need to put in alphabetically. It is entirely coincidental that we have 1, 2, 3 on this compound. Take, for example, this, where we have 3-ethyl, 2-methyl. The locants do not organize the substituents. Alphabetical order organizes the substituents. Whew, okay, that took longer than I thought. What are you guys thinking? You need some practice problems? let's apply some of this. And I'm going to keep the practice problems a little bit more relevant to alkanes and maybe some alkyl halides. But I'm not going to do too much practice problems that have different suffixes. We're going to narrow in our focus. You guys have an idea of how all this nomenclature works. And as we get closer to utilizing those functional groups, we'll come back and reapply those. You know, there's one other exception to naming that I almost never throw your guys' way, and that is if two carbon chains have the same length, and you prioritize the one that has more branching. So if you have an 8-member chain this way and an 8-member chain this way, and the first has 2 methyl groups, and the second has 3 methyl groups, you prioritize the one that is branched more. It's hard for me to come up with an example off the top of my head, but I'll try to put one on the board so you guys see it. There might be one active problem that kind of tricks you like that. It doesn't come up often. Identify the root, identify the suffix, identify what groups are in the prefix and what their locants are.
So, if I start with, is this like the first carbon, 2, 3, would that be like 1 bromo? Then would these be isopropyls?
They are
No,
isopropyls,
would be, since there's 2 of them, would be diisopropyl.
diisopropyl, and then because there are 2 of them, we'd have to say 3,3 diisopropyl.
So why 3 if there's 2 of them?
Well, 3 is their locant position, and they're both on position 3.
Oh, okay.
So then it becomes
if there's 2
3, 3.
thirds because they're both on. Okay.
Yep.
And then cyclohexane.
Mm-hmm.
Okay.
But what I'm going to encourage you to do is list out the locant set that you would get for numbering the way that you did, and then list out the locant set that you would get numbering a different way,
Right.
and choose the lowest locant set.
Okay.
Take a stab at it. See what you think.
I'll do this.
To not be able to draw anything. First, it's close, but if you number it from the other direction, you get a different locant set. And that locant set needs to be compared to the locant set that you have there. So, number it the other way and list what locants that would have, and then compare those 2 sets of locants. We have right now is 1, 3, 3. What would your other set be? Mm-hmm. And which one's lower?
Oh, I just don't know what takes priority.
The lowest local set.
Unless it's like,
These groups equal priority.
okay, that's the only thing I've been having an issue with.
The
Is what groups take priority.
yeah,
I didn't know
for sure.
I just thought that Roman took priority. So alkenes and Roman groups are still.
That's right. Yep. You've added a few too many carbons here. 1, 2, 3, 4, 5. I think it should stop here and then carbons here.
So this.
I've got the right local sets, but now they're not alphabetized. Mm-hmm. Good start.
I'm not sure about this at all.
I don't think that it's a 6
Oh, yeah.
chain. No, which means it can't be on 6. One, two, three, four, 5. You can't start counting from. That's not correct.
Yeah, sure.
Okay. Dimethyl pentane. I don't see 2 cycles. You are right there. I don't see 2 CH3 groups. Okay, actually, there's this cool thing about nomenclature. The name tells us how many carbons are in it. We can derive the chemical formula from the name. Dimethyl, 2 carbons. Cyclopentane, 5 carbons. That's 7. Here's 5. 6, 7, 8, 9. So your name is not matching the chemical formula. All right, in a minute, I'm gonna start working through these with you guys. You got a question?
So, okay, so we just add these at the end, and whichever one's lower, is that what you're saying?
Well, actually, you've got these alphabetized correctly. B comes before I. And then you want to choose the locus set. And this locus set is lower. 1, 1, 3 is lower than 1, 3, 3. So keep them alphabetized and then put in the lowest locus set. What you've done is change the locus set, but then also taken them out of alphabetical order.
Okay, so these don't have to be like, they're not like corresponding.
That's correct.
Okay,
That's correct.
so do 1, 1, Bromo, 3.
Oh, no. Bromo comes first, and bromine is on position 3. 3 bromo.
3, oh, okay.
1, 1.
So I switched these instead of, oh.
Yep. You guys feel your gears burning a little bit? That's good. That's what you want to feel. I'm not sure that the numbers here quite work out. This is 1, 2, 3, 4. Or if this is 1, 2, 3, 4. I think you're either going to have 1, 4, 2, 5. Or you can only talk credit. Yeah, actually, this locate set can be lower if we number it in the other direction. Because instead of starting with a locate at 2, you could start with a locate at 1. Yeah. So,
This is better.
close. But butyl implies a straight chain connected to cyclopentane. But this 4 carbon, no,
Oh, sorry.
we're getting closer.
That would be
your name here, you're calling this the parent chain. 5 is bigger than 4. But also, you're saying that this methyl, which you've already counted in butane, is coming off of it. So you're kind of double counting that carbon. If you guys want to take a quick break to get up and get your blood flowing, this is a good time to do it. And when we come back, we'll walk through the answers for these ones. Yeah.
And
That's
does
it.
that not need?
No, it doesn't. You've got it.
Sorry.
Don't be.
So, with this one, since this is the parent chain, would that just be methyl?
Yeah. Mm-hmm.
Okay.
Except I think it looks like you're counting 6 carbons in the parent.
Oh, fuck.
You're counting up to the bromine.
Yeah,
That was your 6.
yeah. Okay.
Mm.
Because that's what you were talking about earlier today, right? With the conventions.
Mm-hmm.
There is this mean,
Yeah.
right?
So how many carbons in this substituent? 3. Well, here's the carbon in the ring. And then here's a branch that comes off. And here's a
Okay, it's not that full thing.
That's correct.
Okay, so yeah, just, okay. Gee, so then it's just,
Well, propyl implies that it's connected as a linear chain.
isopropyl,
Isopropyl.
di,
Isopropyl.
okay.
Wait.
On this one, 1 bromo.
You know what? I think you lost a carbon. Or 1, 2, 3, 4, 5, 6. Yeah, you had 6 carbons, but they're just connected wrong. There should be a CH2 group.
Never mind. Right?
Mm-hmm.
That's where it is. Okay. But then, it's the right
Oh, you lost the bromine.
two.
And it would have been, I think those would have been 2 CH3 groups, so that would have made it dimethyl. But your name also didn't have bromine in it anywhere. So we got to
follow up on that one.
Yep. Jamie, one of yours was that the bromine? No, actually this one. So if we do the same idea, 4 methyls, 4 carbons, cyclohexane, 6 acetone, 10.
Should I factor in the penton?
Mm-hmm. No, they're actually. I see what you mean. 1, 2, 3, 4, 5. But when you do that, you're counting branches, ring branches, and you can't count both a linear chain and a cyclic carbon at the same
Oh, I was
time.
talking like in the context of this. It's like people here kind of have is there
So
one
sort of-
five?
Yeah, there is, but there's no 5 carbon substituent. So you said your parent is cyclohexane. That includes this carbon.
Oh,
So you can never count that carbon.
in share carbon.
Mhm. So what you actually have are 2 different substituents.
You have 2 different propyl. Sure.
They are 3 carbons, but they're not propyl because that implies a straight chain.
So 1, 2, 3, 1, 2, 3. Why is that not considered a chain?
It is a 3 carbon chain connected by the center carbon rather than a straight 3 carbon chain.
Okay.
And the other thing, by calling them tetramethyl, I see what you mean, 1, 2, 3, 4. You're not naming these 2 carbons. So this name implies 4 and 6, 10.
Yeah.
This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So
Should I do?
look back at the 3 carbon chains, and you're going to use the other name.
I would have 2 sec propyl. That's the group.
It's not sec-propyl, but
Same. I mean, on the
it would be a sec-propyl, but they don't call it that. What do they call it, Sage? Isopropyl.
So it's 2 isopropyl off that carbon.
Yep.
So,
So like in thinking of that, I feel like I'm looking at this incorrectly, and I don't know how to just.
No. Well, let me look at your name again.
Well,
Oh, well, this is the substituent.
yeah.
And how is it connected to the parent chain? It resembles this. 4-carbon chain connected at that secondary carbon.
Okay. Yeah, okay, because you're counting the carbons that come off of this connection. Okay.
Yep.
Can I do diacetyl?
Yes. Okay, a reminder in your naming, halo groups and alkyl groups are of equal priority. So you do not look to put one of them at a lower locant than the other inherently. You consider all possibilities, find the lowest locant set total. Then, if a locant set is tied, prioritize alphabetically, and the halogen groups often come in first alphabetically. Not always, but often. So I want to take you guys through some of these. Number 1, what is my root? Where's the parent chain? Cyclohex. That 6-membered ring is my parent chain. So that has taken out all of these carbons. Now, where am I going to start numbering? Well, either where the alkyl groups are or where the bromine is. So I'm going to show the locant sets that I get for both of these. I just need some more space. Here I will get 1, 3, 3. I have 3 substituents. 2 of them are on the 3rd carbon when I've numbered it this way. If I start where the 2 substituents are and number the other way, then my locant set becomes 1, 1, 3. Do you agree? Which of those sets is a lower locant set? 1, 1, 3. I get more 1s than 3s. It's actually the first or the lowest locant set at the first point of difference, which is right here. They both, numbering both ways, put a substituent at 1. Only numbering this way gives me a difference. 1 is lower than 3.
So it's not the lowest sum then?
It's not the lowest sum, no, but I'm glad you asked that. You don't have to sum them, you just have to go down the order and see which one has the lowest value first. And that's the rule, that's what you go with. Now, the groups are bromo, and then a 3-carbon chain that is connected at the 2nd carbon. So we could call it a sec propyl, but they don't call it that. Instead, they call it isopropyl because it's got the Y. And there are 2 of them. So this compound then is named 3-bromo 1,1-diisopropyl cyclohexane.
Can you do 1,1 methyl ethyl or no?
Yeah, okay, so you could call this 3-bromo 1,1 parentheses, or sorry, di parentheses 1-methyl, oops, I forgot. 1-methyl ethyl cyclohexane. Do you see why there's some preference to call it isopropyl? It looks really awkward being a di-1-methyl ethyl, but that would be the appropriate way to do it. The di would have to go in front of the parentheses because there are 2 of that group, and that group is branched itself. I would prefer this name, but this name is not wrong. You look like you got a question, Maddie?
Can you explain how, I don't see that it's a methyl ethyl.
Well, let's start, I'll do this in another color. Let's start from the parent chain. Here's the carbon that's attached. Here's the longest carbon chain. That's a 2-carbon straight chain
Okay.
with a methyl group coming off of the first carbon attached to the parent chain.
Gosh, okay.
Yep. That's it. Next one. What are my two locant sets? I number from left to right, and I number from right to left. This is going to go back to Rowan's question about is it the lowest sum? If I number from the left to the right, I get 2, 2, 5. If I number from the right to the left, I get 1, 4, 4. We're not looking at the sum, which I think here would be 9. Oh, it would be 9 and 9. Anyways, I don't know. I'm not used to looking at the sum because we don't. What we look for is the lowest locant set at the first point of difference. And there, the lowest locant set is 2 versus 1. Sorry, 1 versus 2. Now we still arrange it alphabetically. So I'm going to have a bromine locant at 1 and a bromine locant at 4. That's 1,4-dibromo, 4-methyl pentane. Prefix, root suffix. Prefixes are gnarly, right? They really don't. They don't give you a break. In my third one, we're either going to number the 4-carbon linear chain or the 5-carbon cyclic chain. 5 carbons beats out 4 carbons. So 2-cyclopentyl butane could work, but that would be the wrong name for the molecule because it chose the wrong parent chain. Instead, we'll call this cyclopentane as the parent chain, with a 4-carbon substituent coming off, connected by that secondary carbon, which is now a tertiary carbon because of how it's bonded. So we call it sec-butyl cyclopentane. Cameron, do I have to say one sec-butyl cyclopentane to describe where the substituent comes off of the ring?
No, because it can come off of any corners.
All of those positions are the same. There's one substituent. I don't have to provide the locant. That's another place where we don't have to be redundant, but you can. You can just as easily call this one sec-butyl cyclopentane. It's just no different than sec-butyl cyclopentane. What would be the other systematic way to name this? 1-methylpropyl cyclopentane. I think in this case, you actually wouldn't need the parentheses because what parentheses are good at is having you list a locant for where the branched substituent is and not have it be confused with the locant of where the branching is on the branch. So I think you could just name this without the parentheses, but why would you do it anyways? Sec-butyl cyclopentane is going to be easier. Okay, now this is not something you're going to run across often, but in this bottom molecule, there are 2 carbon chains of equal length. And one of them has more substituents than the other. So let's look at this 1, 2, 3, 4, 5, 6. What I get here is 2-methyl, 4-isopropyl hexane. But if I number it 1, 2, 3, 4, 5, 6, I still have a hexane chain, but now I have 3-ethyl, 2,5-dimethyl hexane. Blue has 2 substituents, red has 3. And so the preferred IUPAC name, and this is not one that I'm going to give you guys a lot, but I want you to know it because it shows up on the homework. Preferred has more substituents. One other cool thing about nomenclature is that you can derive the chemical formula out of the nomenclature. Nomenclature tells you exactly how many carbons are in the structure. Methyl, 1. Isopropyl, 3. Hexane, 6. That's a total of 10 carbons. Ethyl, 2. Dimethyl, 2. Hexane, 10. Sorry, 6. 2, 2, 6, 10. This means you've got a proof, a way to check. If your compound has a different chemical formula than the name you gave it, then you named it wrong, whether that's too many or too few carbons. One thing that you will need to be able to do in this section in evaluating nomenclature is to be able to draw a structure based on its name a structure based on its drawing, provide a root, a suffix, a prefix, a locant. But there's one other aspect. One thing that I really love to do with this is to give you the wrong nomenclature. Have you draw it, and then determine what was wrong about it and improve the name. So I'm going to have us do a problem like that right now.
And sorry, I think I missed it, but both names of that would be fine as they both come out with 10 carbons. It's like even.
So both names are meaningful, but one of them is IUPAC accepted, the one that has more branching.
Okay.
You notice they have the same parent chain, hexane. The only difference is methyl and isopropyl versus ethyl, methyl, methyl.
And so since it's like
They prefer more substituents on the parent chain. That's one that we'll see the least often. So can you draw this compound based on the name? Can you identify what's wrong with it? And then can you rename it? Here's another one to do. Isopropyl ethane. Draw the compound based on the name, recognize what's wrong with the nomenclature, redraw it, or rename it. Good. Rename it. Identify what's wrong with the name. Rename it. Yes. Yes. Good. Good. Yep. Good. You got 1,5. Sorry, you got 1,155 tetramethyl. There you go. That's it. and the way that you're changing it, that's the way to do it. Yep. That's the correct name, but that doesn't agree with that structure. Actually, that's correct.
Oh, sorry. Yeah.
Okay.
I had to rewrite that.
Yeah, what you did was
this
2 isopropyl
one. Yeah, I
proteins.
accidentally put.
Yep. 1 and 5 on cyclopentane are going to be next to each other rather than the same. To have them on the same, I think we have to do like 1, 6, and go all the way around and come back. Yep. Good. Yes. So can you put to words what was wrong with them?
Yeah.
Good. Yep. You got it. You've drawn it right. Now can you rename? Thing about renaming, don't pay attention to the name that you were given at all. Because you might not know what they identified wrong. Ignore that name. Use your skills again. Identify the root. Identify the suffix. Identify the substituents. Find the lowest locant set.
Can you like assume alkane until proven otherwise?
Oh, you know what? Part of these names, like something I can't give you wrong, is the wrong chemical formula. Right? And so like, I can't say this is cyclopentane, but it's actually cyclopentene. It just wouldn't work. It's kind of like this. Both of these names work, but one is preferred. If I had said this was instead pentane, that's
wrong.
Yeah, it's just wrong. You would change the chemical formula and have to impact that. Yeah. All right, I'm going to go ahead and start drawing these up. Cyclopentane, that's where I'm going to start. I'm going to draw my parent chain, 5-membered ring. Then I'll look at my substituents, 2 methyl groups, one on position 1, one on 5. Does it matter where 1 is? No. So I'm gonna start here. Does it matter which way I rotate? No. So I'm gonna rotate this way. 1, 2, 3, 4, 5. There's my compound. So what's wrong with the name? It should have a lower locant set. So what's a better name for it? 1,2-dimethyl cyclopentane. Okay, wrong locant set. Start with my root, ethane. Boop. Isopropyl. Why is there no locant? Because it doesn't matter. If it's not on one, it's on the other. So isopropyl, coming off of one of them, of my 2-carbon chain. There, got it. Okay, so what's the problem with the name? Not 3 carbons. The longest parent chain won't be 3 carbons. 4 carbons. 1, 2, 3, 4. So the issue was the parent chain. The wrong parent chain was chosen. So should it be 3-methylbutane? Yeah, I've numbered it the wrong way. So if I number my carbon chain the opposite way, 2 is a lower locant than 3. 2-methylbutane. So here are the most common ways that these occur. You get the wrong locant set. You get the wrong parent chain. What might be another common thing that shows up? You alphabetize wrong. That would be the only other common error. I don't know how to spell alphabet anymore. In an alphabetical problem, all of the groups are named correctly, all of the locants are correct, but the alphabetical order is just listed wrong. I'll be honest that I tend towards these two because I find this issue to be more meaningful than having a wrong alphabetical order. So one of our learning objectives is, by the end of this, I want you to be able to evaluate nomenclature. And that goes forward and backwards. And to be able to take a wrong name, still interpret the structure, and identify how to name it correctly. Identify what the wrong name was. If you look at your midterm exam, you'll see a problem like that. Draw the compound, rename it, identify what's wrong. Your unit test will have a problem like that. It gives me, I think, the best opportunity to say how well you understand both your ability to draw and name. Now, I thought that we would finish that in 30 minutes. We finished it in 60 minutes. Nope, sorry. An hour and 30 minutes, like 90 minutes. So hopefully you guys are feeling confident on it because we spent a lot of time. I want to set us up for our class next week because we've got some really fun concepts to explore, and it's better to plant this in your mind now than to wait. So on our homepage, if you scroll down, you'll find a link to kimtube3d.com. I like kimtube3d because you can take a lot of molecules and look at them in 3 dimensions. You can move them around, you can play with them. This is the part of the semester where if you don't have a modeling kit, you might want to get a modeling kit. You might want to invest in one so that you can visualize these structures better. You scroll down further on our homepage, it will bring you to simotter.com. You'll have to switch from point group to molecule type, and then you can explore a lot of different organic molecules. So, to set us up, there are 3 main types of perspectives. This is truly the art class part of organic chemistry. There's 3 main ways to view a molecule. One of them is actually, I'm not counting here, one of them is the perspective. I would say that our standard way is to look at a structure and use those wedges and dashes to say things are coming towards me, things are going away from me, and things are in plane. So that's our standard. Here's some of the other types. One is called sawhorse. I don't like sawhorse. I think it's clumsy and awkward to look at, and it's not beneficial. Sawhorse will take your standard perspective, things coming towards you and away from you, and it will kind of twist it so that they all look like they're flat. So sawhorse takes this drawing, and then it turns it into this. These are my CH3 groups up here. It kind of elongates a specific carbon-carbon bond and then shows all of the other groups as flat against that. I do want you to notice something about the perspective. Up at this carbon, there's a methyl group that's literally being drawn down on the board. And then there are 2 hydrogens that are drawn, pointed up on the board, one of them towards, one away. In the sawhorse, we preserve some of that. This methyl group that was coming down is still coming down. And this methyl group on the front carbon is still going up. So the spatial arrangement is preserved, but squished. I don't like it. We're not going to spend a lot of time with it. I do want you to recognize you could still name the compound from the sawhorse projection. It's not any more challenging than naming it from a bond-blind structure. The other way that these structures are shown is called the Fisher projection. This is something that you would use a lot more in biochemistry. It's used a lot with sugars. If we took this compound and showed its Fisher projection, the first thing that Fisher does is it rotates the bond line so that it's no longer zigzag and it becomes zig-zig, which means that all of your carbon chain is kind of pointed in one direction and all of your other groups are kind of pointed in one direction. And then what Fisher projection does is it sets your perspective, that's an eyeball, sets your perspective at this carbon chain backbone. So there's a lot of assumed spatial arrangement, a lot of assumed stereochemistry, and it gives us this. CH3 at the top, CH3 at the bottom. And there is an assumption here about stereochemistry. It's actually saying that the bonds to the CH3 groups are going away from your perspective. And all of these bonds that are horizontal are actually coming towards you. Because you're looking at this bent thing from the top. And so you're seeing things going away and you're seeing things coming towards you. But Fisher projection just flattens that out. If you look up sugars, linear sugars, you'll see this a lot. And this is similar to the Hawthorne projection, which is used for cyclic sugars. There's a lot of assumed stereochemistry. All right, the last one, and the one that we're going to look at the most, is the Newman projection. And what we'll do here is cite down a carbon-carbon bond. So on this molecule for butane, let's take our perspective and set it down this carbon-carbon bond, specifically from this angle. What the Newman projection gives us is a dot for a front carbon and a circle for a back carbon. That's because if you truly eclipse it, like what you're looking at here on SimOtter, you wouldn't see the back carbon. So we show the front carbon as a dot and the back carbon as a circle. And then you show the groups coming off of it. All right, well, here's how I like to take myself into the plane of the board. I'm going to grab hold onto the wedge and the dash. And I'm going to use that to pull me into the plane of the board. So what I've done right now is I've grabbed an H and an H. And I have a methyl group that's coming straight down. And I'm going to take that out and snap them in. That's my front carbon. So I have an H and an H that are going straight up. And I have this methyl group on my front carbon that is going straight down. And now I'll do the same thing on the other side. Grab the H that's coming out, grab the H that's going behind, pull that out of the board and snap it down. That's connected to the back carbon. And what's coming straight up from the back carbon is a CH3. If you take a look at the molecule we have over here, you can kind of see this 6 points coming off, 3 from each carbon. Group in the back that's going straight up, group in the front that's going straight down. That's similar to this Newman projection that we've got here. This is called a conformation. It's a way that it can take up space. And on Tuesday, we're going to look at the energy cost associated with conformations. We're going to look at how to draw different conformations and predict which are higher energy and which are lower energy, because molecules are always moving, but sometimes they are moving in preferred lower energetic ways. Then we're going to look at the same type of thing for chairs. For rings. We're going to look at 6-membered rings and the way that they take up space. And then Wednesday and Thursday, we're going to do section 5. And section 5 is kind of all about locked-in spatial arrangement, locked-in stereochemistry, and the differences that can cause in molecules. Okay. Have a great weekend, guys. I'll see you on Tuesday.